Some of the things that you want to ask yourself whenever you're doing synthesis, and there are multiple ways to approach multi-step synthesis. I would say a good place to start is, can you spot the difference between the starting material and the product? Right, so you need to kind of account for what has changed, what is the same, right? So I ask, what are the atoms or groups that have left the molecule? What are the atoms or groups that have been introduced into the molecule? One strategy that can work is consider working one step backwards, right? So if you look at the products, both products are alkenes, right? What's the only way that you know of to make an alkene? What's the only type of reaction that you can use to make an alkene?
From alcohol, we can use H2SO4.
I mean, that's more specific, right? I was going for more of
elimination.
Excellent, right? Just general elimination reactions, right? So, for example, if you were asked to make something that looks like this, right, you would probably propose a starting material that has this general structure or that general structure, right? You know you need some leaving group, and then depending upon what that leaving group is, you can decide whether you need, if it's just an OH, maybe you need to protonate it, form water. If it's a halide, maybe you just apply a base, right? But you can often think one step backwards in order to shorten the overall synthesis. Okay, so if you can imagine a starting material that we can make use from, it's not necessarily a specific starting material, right? Just a general structure, right? And the third thing that you want to consider, kind of relates to the first, is can you see the carbon structure, and the starting material carbon structure in the product? If you can, that's going to allow you to see where the reactions take place, right? What atoms are actually reacting, right? So you can see here we have a 5-membered ring in the starting material. Those 5 carbons are in the product as well, right? So we're not breaking the ring open, right? It's likely something that's going to happen, and really the only change that's taking place is at this atom, right? We're attaching a new carbon to that atom, right? Getting rid of the oxygen, changing to a double bond, right? So most of the chemistry is probably going to happen on that atom, but you need to be able to see, right, what's the relationship between this structure and this structure, and what hasn't changed, what's still there. Questions about that? Okay, as we go through multi-step synthesis, right, we might introduce more strategies, because you don't have to necessarily think of every multi-step synthesis or approach every multi-step synthesis the same way. Sometimes it's going to be easier to see the starting material structure in the product. Sometimes it's going to be really difficult. So just keep that in mind. All right, so what are people thinking for these syntheses? What are some ideas you have? Not necessarily answers, but what are some of the things that you paid attention to whenever you figured these issues out? Yeah.
And this oxygen's gone, so I think we need a possible water leading group.
Excellent, right? So we need to, you can see that this oxygen is no longer in either of the products, right? And so we're probably going to have to kick that out, somehow turning it into a leading group. So that could be in terms of water, right? But we also saw the other day how oxygen can be incorporated into other types of leading groups. So we're not, just restricted to a water leading group. Yeah.
Kind of to follow Anna, I was thinking maybe like a primary step could be like the reduction.
Okay, so why do you think that?
So she was explaining that water could be a leading group. So I was thinking that maybe we could make a reduction, and then that would turn into an alcohol.
Great, yeah, so in order for the oxygen to be a leading group, right, the only way we've seen that is when that oxygen is part of an alcohol or part of an ether, right, but definitely not part of a carbonyl. We can't just make an oxygen of a carbonyl, leave in one step, right? So do that would be to reduce that carbonyl bond, and what are options do we have for that?
I use the AL or the LiB4.
Okay, so if we do that, use lithium aluminum hydride. It's two-step process, so we add the reducing agent and then we have to work it up with water. That's going to be the product that we make. Okay, and that's right. So in order for any elimination to take place, we definitely need to reduce the ketone down to the alcohol. Right? If you look at the products, what is being added into the product? What extra atom or what extra group is being added to make the product? A methyl group, right? And so here, the addition with lithium aluminum hydride is going to be a hydride, a hydrogen. Right, but that's not going to allow us to introduce that carbon very easily. Okay, so you're on the right track in thinking about reduction, but what type of nucleophile would we need to add rather than a hydride nucleophile? If we want to introduce a carbon group.
Can we use a Grignard?
A Grignard, yeah, excellent, yeah. And so that's the direction that we want to go. Okay, so you can see in the product, if this is the carbon that has the carbonyl on it, oxygen, right? Then we need to add a carbon or methyl group to that carbon, while that carbon is still electrophilic. So we'll start with the ketone. First step is going to be Grignard addition. We usually do Grignard reactions in tetrahydrofuran solvent. And then we have to work them up with water, usually a little bit of acid. Okay, and that's going to get us to the ring with two methyl groups on it. Right, so this is going to be the same for both reactions. Right? This is how both of the syntheses will begin. Any questions? Everybody's comfortable with the mechanism, seeing how the Grignard adds to the ketone? Yep. Okay. So where do we go from here? So let's focus on the top synthesis, right? We only have two steps, and we figure out what one of them is already. So how would we get to that product of the two-step synthesis from here? Yeah.
Would you coordinate the OH group and then use the hydrogen on the bottom of the carbon to form that double bond to kick off the water?
Okay. So what were so you're right mechanistically, what would the conditions of that be? Acidic? Okay. So we can say this is a dehydration reaction, right? We're losing water. And for dehydration reactions and elimination, we're just adding an acid, H2SO4, and then we're going to heat this up, right? We don't want to add water because water is going to be a nucleophile, right? If we're trying to get rid of water through dehydration, we don't want to add water back in, right? Same thing with alcohols. We don't want to use an alcohol solvent because when this water leaves, if we have a bunch of alcohol around, that alcohol will add back in to make it, right? And that's not to say we won't make the elimination product. It's just to say that if we want to maximize the elimination product, have it be the major or only product, right? These are the conditions that we would want to use. Any questions about this? No? Okay, So this is going to proceed through an E1 elimination. And remember, E1 eliminations are reversible and result in the formation of the thermodynamic product at the most stable and lowest energy. Questions?
What's gonna act as the base to pull off the hydrogen?
Sure, so in this case, we'll have an OSO4H minus, right, that can act as the base. But probably more likely, we're gonna have other alcohol groups act as the base, right? So in essence, we can kind of think of this as a catalyst, right? It donates the proton to the first oxygen, forms water, and then this oxygen is going to pick up a proton from another molecule here, right, which will form water there, right? It's kind of a chain reaction after that. Okay, other questions? Okay, what about the three-step synthesis? So we'll start off the same way, form the tertiary alcohol. But if you look at the three-step synthesis, we're forming a different regioisomer of that alkene, right? Rather than the alkene forming the thermodynamic product, where the alkene is in the ring, right? The alkene is formed down this carbon bond. So how would we accomplish that? So it's the major product. So let me simplify this for you a little bit, right? So if we think about this starting material with an iodide leaving group, right? This can result in the formation of two different alkenes if we do an elimination, right? So the thermodynamic product, the more stable alkene, we call that the Zaitsev product, and that just deals with a Russian chemist who was studying these elimination reactions and found that the more substituted alkene in his reactions, right? The more substituted alkene was a major alkene. Zaitsev, you'll find spelled 3 or 4 different ways. I'm not worried if you know Zaitsev or Hoffman. They're just names. I'm more worried about whether you can justify why an alkene forms the way it does, right? And then the alkene can form down the other bond. We would usually refer to that as the kinetic product, right? The one that forms fastest, right? And that's referred to as the Hoffman product, just because an old German chemist, when he was doing his studies, he found that in his studies, the less substituted alkene was the major product, right? So historically, we've just continued to refer to them as the Hoffman and Zaitsev alkenes, just to talk about the difference in regiochemistry. Okay, so how would we accomplish these things? Why, how would we set up this reaction so the Zaitsev product forms versus the Hoffman product? Yeah.
What we did, we used a bulky base that wouldn't interact.
Right. So in order to form the less substituted alkene, we increase the size of the base, right? And that's going to preferentially pull the more available protons, right? The protons that are farther on the outside of the molecule, right? The ones that are easier to get to, right? And if we use a small base, say methoxide, right? The methoxide is going to form the thermodynamic product preferentially because that small base is able to pluck off that proton there, right? So those two protons, pulling those two protons would lead to the two different products. Okay. It's notable that both of these are going to be E2 processes. That's really the only or the best way to control regiochemistry in elimination, right? By doing E2 reaction and varying the base in order to get the result that we want. E1 reactions, as I said before, usually result in the thermodynamic product because those reactions are reversible. Right? So eventually everything just kind of goes to the most stable product. Right, so knowing this, right, and understanding that OH minus is a bad leaving group on its own. Yep.
Could you use I don't know the name of it, but could you use HI to turn that into a halogen and then use NaOET to turn the halogen into the double one?
Sure, yeah, so that's one option. Right, I would say, so that's possible, right? I would say the one problem with this is that this step here is going to be an SN1 reaction, right? Going to create carbocations, and often carbocations will lead to things that we don't want, right? Will lead to the product, sure, but will also lead to things that we don't want. Rearrangements, right? Carbocations are just extremely, because they're low valent carbon, they're extremely reactive, right? And that's when we see rearrangements, right? The 1,2 alkyl shifts, 1,2 hydride shifts, and things reacting the way we don't necessarily want them to, right? So what's a better option than turning this into an iodide? What's another leaving group we can turn that oxygen into that doesn't involve cation formation? Yeah.
Water.
So again, water is going to be a unimolecular process, right? So that's what happened here. Oh, that doesn't lead to that product. My bad. All right, so this is a unimolecular process. We form water leaves, cation forms, and we get to the most stable alkene. Yep.
What if you use NaIN anaerobic?
Well, we have oxygen, or if we use sodium iodide, we don't have a good leaving group to kick it out with. Right? Yeah.
What if we use tosylate?
Awesome. So sulfonate esters, right? That's kind of the secret to a lot of things. So rather than going and doing HI, we'll add tosyl chloride, triethylamine, a pyridine, right? Some amine base. That's going to give us a tosylate leaving group, right? This tosylate leaving group is very much like iodide, like bromide, like any halide, right? So now we have a good leaving group, and as long as we choose the right base, then that's going to lead us to the kinetic elimination product. Right, so sulfonate leading groups, right? Formation of tosylate, mesylate, triplates, right? They'll often help us avoid formation of carbocations, right? Because we're not forming water, we don't need to replace water with a different different leading group, right? Or we're not doing elimination directly with water. So. Questions about this? Right, so hopefully all this kind of points to the fact that alcohols are an important functional group. Right? We can use them in substitution, we can use them in elimination. We've seen how they work in other reactions, right? So alcohols are part of acetal and ketal formation. Alcohols are part of esterification reactions, right? Substitution, elimination. So knowing how to make them or recognizing how to make them, organizing the reactions to make them is going to be kind of important. So let's just really quickly review the different ways we know to make alcohols. First, it's just going to be addition of hydride nucleophiles to carbonyls, right? We're not going to go over every specific hydride addition reaction, but if we take if we take a ketone, for example, and treat that ketone with sodium borohydride in an alcohol solvent. Right, that's going to result in the formation of a new carbon-hydrogen bond. Through the nucleophilic addition of that hydride to the carbonyl carbon. Questions about hydride nucleophiles, right? So we learned a couple of different reagents for hydride nucleophiles, lithium aluminum hydride and sodium borohydride. Right? You can also think of alcohol formation through the lens of additions of carbon nucleophiles to carbonyls. So in this, I'll show an example where we start with an ester. And we'll add phenyl magnesium bromide, work this up with water, acid. going to lead to the tertiary alcohol shown on the board, right? And so if we think about this mechanistically, with esters, hopefully everybody can reason out a mechanism, right? But this is going to go through one addition. To make a ketone intermediate, right? And then the ketone that forms in that reaction, being more electrophilic, is going to react with with another equivalent of the Grignard, right? So we get two phenyl groups on this carbon. Right, we can think of reactions where we're doing nucleophilic substitution, right? Reactions we learned more recently with hydroxide or water. Right, so if we just take an alkyl, primary alkyl halide, treat that with sodium hydroxide, right, that's going to result primarily, as long as we keep the reaction cold, in a substitution reaction. We'll keep things simple, actually. Right, and that's pretty much the only ways that we know of to make alcohols, right? Through the additions of nucleophiles and carbonyls, right, and nucleophilic substitution. Right, what I wanted to go over today, and we don't have too much time to really talk about it. Going to be going the other direction, right? If we take an alcohol, what can we do with that alcohol, right? What reactions do we know? And one of the reactions that we haven't talked about yet is the oxidation of the alcohol to a carbonyl. Right, so this is going to be an oxidation or oxidation conditions that we refer to as the Jones oxidation. Right, you can see the conditions are somewhat harsh. Na2Cr2O7, this is sodium dichromate. So that's the structure of sodium dichromate. If we have time today, we'll go over the mechanism, but I don't know if we'll actually get through the mechanism today. Right, in this reaction, you can see that I'm starting with a secondary alcohol. Right, and the product that I'm making is a ketone. If I change this up and I start with a primary alcohol, apply the same reaction conditions. See, the functional group that results is going to be different. Right? So oxidation of a primary alcohol under Jones conditions results in the formation of a carboxylic acid. Right? Functionally, these are both accomplishing the same thing, right? Which is increasing the number of carbon-oxygen bonds, right? And that's what, when we're thinking about oxidation in organic chemistry, that's what oxidation is, right? Increasing the number of bonds from carbon to a more electronegative atom, right? It doesn't have to be oxygen, but in this case, it is, right? So here, we're starting with one bond to oxygen, right? And in the product, that same carbon now has two bonds to oxygen, right? Here again, we're starting with one bond to oxygen. In the product, that carbon has three bonds to oxygen. And so what's changing really is not necessarily just the bonds to oxygen, but also the bonds to hydrogen. Right, so you can see the starting material, the alcohol that has one bond to hydrogen, can only gain one other bond to oxygen. Right, so we can't oxidize beyond a ketone for a secondary alcohol because we only have one hydride or one hydrogen to lose. Right, and then for the primary alcohol, we have two hydrogens. Right, so we could replace the bonds to both of those hydrogens with bonds to oxygen. Right, but this is very reagent specific. This will be the last thing we go over, and then we'll, if you want to look up the mechanism in the book before Friday, that'd be great. Otherwise, we'll go over the mechanism on Friday in class. If we take that same primary alcohol, and use a different oxidant, we can control the oxidation so we are only gaining one bond to oxygen. Right, so go from the primary alcohol, oxidize it to the aldehyde. And we use a reagent called PCC, which stands for pyridinium chlorochromate. Right, and this is significant because just like the dichromate above, it's a chromium reagent, a chromium oxidant. Okay. On Friday we'll talk more about why that's special. Chromium's at the same oxidation state here as it is in the reagent above, right? So we're starting with chromium at oxidation state 6, just meaning that there are 6 things attached to that chromium. Right, but by changing the structure of the oxidant, changing the conditions under which the oxidation is run, we achieve a more controllable oxidation. Right? So we can stop specifically at the aldehyde without over-oxidizing. Right? And we think about synthesis, this gives us a lot of options, right? If we can take the same alcohol and do 2 different types of oxidations with it. All right, so we'll come back to this on Friday. Like I said, if you have a chance to go through that, it's like 1 page or 2 pages in the book. Read about oxidations that we'll do.